All right, well, welcome everybody to the May 2024 meeting of the Mornington Peninsula Astronomical Society. And as usual, I'll go quickly through a couple of things. We'll begin with the centre at the top there, showing the Lego model of the Artemis launch system, which Lego released today. And if you haven't ordered yours now, you better hurry before they all run out. And you can see the size of it relative to the lady up there, so quite a lot of pieces, probably a few thousand in there, I would think, to do that. Next one down in the left-hand side there was one of SpaceX's competitors, which is AST Space Mobile, has teamed up with Google to go one better than Starlink, and they're promising a constellation of satellites that will communicate directly with mobile phones without having to buy an intermediate box of technology on the ground to pick up their satellites. So they just did a proof of concept of that back in January, and that seemed to have passed all the tests. So they're seriously now going to be taking on Starlink, and it probably means another constellation of launches as well into low Earth orbit. So they were promising, certainly of the Australian continent, that they will cover 98.5% of the area, just direct to ordinary mobile phones, which is pretty impressive. I won't talk very much about the Aurora that occurred a couple of days ago, as some of the others coming after me will no doubt talk about that in some detail. But I'll show a couple of photos from the last bright one that we had here. These couple of photos over on the right hand side I took, and it was also a Saturday night. This is back in 2001, so we're talking about 23 years ago since the last bright one. The one that was visible just a couple of days ago only got up to a KP value of 8 for the Australia region. I think the planetary value got up to about 9, but here in Australia it only got up to 8, whereas that one was actually a 9. And at the time, I had my whole family down here. They literally were laying on the concrete slabs outside, just looking at the show going on overhead, because it was lighting up the sky reds. And depending on the photograph that you took, because in those days this is all pre-digital, so those were actually Ektachrome slide film at the time, and depending on your film and how it was developed depended on whether you got reds or oranges or pinks. And as you can see the difference here, this was me taking it slightly different times in a slightly different direction, exactly the same film, same camera, same developing, and you see this one comes out with pinks. And this one, I think, tended to smear out a bit because these were 20-second exposures. And so you see a curtain of red down to the south, which is over there in the sky. And you're not actually seeing a lot of the detail there because it has actually moved during the time. And of course, this is in the era when you then had to wait a week while your slide film was sent off for processing, and you bit your nails at the time as to whether you got it right or whether it was going to be a total disaster, unlike today with the digital. You'll notice here that a KP of 9, which is these ones here, should be visible equatorially at the tropics. So in other words, you'd be able to see that almost up to the equator. So really, really bright, and indeed that one was really, really bright at the time. And I had my in-laws here as well. They were also watching it, George and Thurley Fowler, and they both recently deceased actually by coincidence just in recent weeks. And they said it was the most spectacular thing they'd ever seen in the sky. So these very bright auroral events tend to be once or twice in a lifetime that you're likely to see them. So if you get another chance to see one of these bright aurora, don't put it off. Make an effort. And there certainly is hope, because you see this picture of the sun here. The sun actually does rotate, and where the active part of the sun that gave rise to the aurora from the other day occurred, it occurs like a water sprinkler on a lawn that is rotating around spraying water, and if you're in the way of the beam of water, then you're going to get wet. Now what has happened is what gave rise to the aurora the other day has now rotated round slightly, and in about 27 days it's going to come into view again, which means in about 27 days time, if that active region of the sun is still active enough, you can get an encore performance. It probably is not going to be as bright because it would have released some of its energy, or much of its energy, over those couple of weeks beforehand, but there is nevertheless hope there. So from last Saturday, add about 27 days plus or minus, and put that in your diaries, and you might be lucky enough to see it again. So tonight, welcome everybody, and we've had a number of new members. So I'll read out their names since we last met. There's Dennis Cook and Mary Connolly, Philip Cook, Adele Talbot and family, Fiona Holmwood and family, Aaron Lee, Jane Suffield, and Finuella Manelli and Richard Cusack. Are any of those here tonight? Oh. Welcome to the Society. Ordinarily I'd point you to the new members officer, but because she has to get up for work at 4:30 in the morning at the moment, she's not able to come to these meetings, so I won't point you to those. Instead, what I'll do is I'll ask any of the committee members here to put up their hands. So if you can look around and just say hello during the tea break, and we'll try not to ignore you. So welcome to the Society, and ask anything as you like as we go along. Now, before I move on to the other things, I'll just explain a little bit about the aurora. Now, why you're seeing the colours of the aurora is we're getting down into a bit of quantum physics here, and that's because what you're seeing is the particles from the sun, mostly electrons, cause the atoms in the upper atmosphere, which are mainly oxygen and nitrogen, which you'll see a little bit later in the main talk, causes them to go up in excitation. So in other words, it's like consider the rungs of a ladder, and if the atom actually absorbs the light from the sun, or the energy from the sun, from the electrons hitting us, it will move up, say, 4 or 5 rungs of the ladder all at once, and then within a few nanoseconds it will drop back down. And normally it doesn't drop back down all 4 or 5 rungs, it may only drop down 1 or 2 rungs at a time. So consequently, the energy of the light that it gives out, which is the light that you see of an aurora, is only a small part of the total energy that actually pushed it up the ladder to start with. And I can show you a bit of a demonstration with that. This little bit of what looks like Art Deco glassware is called uranium glass, and for a very good reason. It actually has uranium in it. And the uranium that they used to make these was actually entirely cordoned off during the Manhattan Project in the Second World War, as they diverted everything towards making the atomic bomb. So you couldn't make this stuff during that time. And while the Cold War was still on, they were diverting all the uranium as well to nuclear weapons production, actually. And again, you could not get uranium for putting in uranium glass. But after the Cold War was over, it became a little bit more available. And what I'll show you, if I have it, is I have a little torch here. This actually came from a COVID-19 test kit, and it's an ultraviolet torch. So if I turn it on and shine it at you, you probably aren't going to see much colour at all, because that is shining very brightly in ultraviolet light. Right, so you can't see that much. But if I hold it up to the uranium glass, all of a sudden you can see the beam of light is causing the uranium to fluoresce. So in other words, the ultraviolet light from the COVID-19 test lamp is actually high energy light. It's causing the atoms of the uranium in here to go up to an excited state, and then they're dropping back down, but not dropping all the way down the ladder, otherwise they emit light in the ultraviolet. But instead they're emitting it at lower energy, which is in the green part of the spectrum there. So that green colour is actually characteristic of the Uranian glass. And some of the Uranian glass typically has between 1% and even 25% uranium in it. And yes, it can be radioactive if you have a sensitive enough detector.
So does the rest of the energy, we're only seeing the green part,
yep.
Does the rest of the energy for red or something?
Yes, you would lose it either as heat, or in some cases, if it didn't go all the way down to the bottom of the ladder, you might get a second drop down the ladder, so you get more light given off. So it's not necessarily the once. So what you're seeing there is a case of fluorescence.
Put it in a crystal ball and become a clairvoyant, you'll be...
Yes. So you were able to see that glowing okay with that light down? Yep. So that's effectively what the aurora is. It's being excited by light up to a higher energy level, the atoms up there, and then as they drop back down, they're giving light of a lower energy. So you're talking about the greens and the yellows and really low energy down at the red end of things. Okay, so I'll look at the events of the past month and the coming month. Then I'll throw over to Chris for AstroMoPho and Guido for Sky for the month. Then we'll look at space storms in the upper atmosphere. And I thought I'd throw that one in, given that that's all to do with aurora and space weather. And here in Australia, the Bureau of Meteorology these days actually looks after the space weather side of things. It used to be a separate organisation. And then we had a visitor to the Briars back in 2016, Amy Shearer-Teagle. And I'll show a clip that goes for about 5 or 6 minutes on why the Apollo missions flew in a figure-8 shape when they went to the moon. She explains what the reason was, and that carries on from the talk that we have from Stephen Slater, where he actually showed that figure-8 back in March when he was here. And then we'll close at the end of that and look at why life came into existence here on Earth. So recent events, there was Working Bee the Saturday after this meeting back in April. Then we had the Balcombe Rovers, which is senior scouts here at the Briars on the 22nd of April, and we had 20 odd scouts here, and they had a lovely cloud-free night, had a good time. Then we had a committee meeting by Zoom and talked about a few things, including staff viewing night for the Briars, which is coming up soon. The Scout Cubs and Guides night was called off as we didn't have any bookings, so that is what happens if we don't get any bookings a couple of days out. Then we had a long range viewing night all the way out to Phillip Island down by Cowes, where we had 75 year 3 and 4 pupils, so that's mid-primary school level. We're visiting there from Geelong, so they'd been bused all the way along from Geelong. We were the entertainment on their first night on camp. So in other words, they were really tired on the first night and we had to amuse them for the evening, which is no small task. Fortunately for them, there was no cloud that evening and they had a great view outside despite all the flood lighting that got in the way of the telescope seeing at least fainter objects. Then on the 3rd of May, we had public stargazing here at the Briars with Guido giving the talk there, and they had a little bit of cloud for some of the evening, but not enough to dampen the enthusiasm. So coming up soon, this weekend we've got on Saturday the Working Bee at the Briars as usual. Committee meeting will be on Zoom next Tuesday if anyone's interested to dial into that and listen to it. Any financial members welcome to listen in. We've got a repeat of the Scouts, Cubs and Guides night that Friday on the 24th of May. Currently we have no bookings, so if we keep on having no bookings, then we'll call that night off just beforehand. 31st of May, which is the following Friday, we've got the Briars staff. They're the staff who actually work here at the Briars, are coming along for a viewing night just for them and their families. And Guido's will be giving the talk to them. 7th of June, Trevor's back from overseas now, so he'll be talking at the public stargazing night all about the eclipse and he'll also talk at this meeting next month about the solar eclipse he went to in the US and Mexico recently. Then the next meeting here is the monthly meeting on the 19th of June. And I put on the end there, we have a big viewing night coming up for Kringle Primary School with 220 pupils there. It's the entire primary school, so we're going to need quite a few telescopes for that one. So please, please do put that in your diary for the 20th of June, which is a Thursday.
Is this all in one night, or are you going to split?
This is all in one night, and you'll notice the start time of 5:30 p.m. That will be when the talk starts, and so telescopes will be needed by 6:30 p.m. for that one. So in other words, I've got to do the song and the dance out the front for the first hour, and before handing over. And with that, I'll throw over to Chris.
All right, so welcome to AstroMoPho number 15. And for the uninitiated, AstroMoPho is the monthly photo challenge that we do here at MPAS, where we are given a topic to photograph, and members then go out and shoot that target. This one was Delta T, or witnessing change over time, and it was a bit prophetic of me, as we ended up getting a few good things to image, comets and even a bright aurora. This first image, and I've left my pointer over there, haven't I? It's in my hat. Thank you. First image here is by Russell Smith of the Aurora the other night from Frankston Beach. It's not really a MoPho image, but I've just put it on there because it's topical of because of the Aurora. And also something interesting to note, and that is the SAR arc, which is visible in this photo over here. So an SAR arc is something that I didn't know about up until a few days ago. And what it is, SAR stands for Stable Auroral Red Arc. And it happens during intense auroral activity where part of the upper atmosphere is energized in relation to the aurora, but it's not glowing for the same reason as the aurora. As Peter explained, the aurora glows because of the ionized molecules. However, the SAR arc is actually glowing because it is due to kinetic energy and heat. By the auroral activity, there's an electrical current flowing around the Earth that gets supercharged at times of strong geomagnetic activity and glows red. And it is witnessed around auroras of this type, and it has actually shown up in a couple of the other photos that we'll see later on. So I'll point it out. Sorry?
You get many spectators down there.
At Frankston, I wasn't at Frankston. I think it was pretty good that night, but the next night though, it was even busier, but nothing to see. So I think yeah, everyone got wind of it and went the next night, but no, it was pretty busy everywhere. Now where's this pointer gone? Okay. All right, so this challenge, we had quite a few people finishing this challenge. Dominic Lucarelli, Greg Walton, Peter Lavelle, Chris Kostokanellis, Guido Tack, Sylvie Grandad, Dominic Martello, Philip Holt, Chris Blackley, Hornsby, Jamie Pole. I think this is probably the longest attendance list we've had for one of these, so well done, everyone. And here is I'm just using these photos to show them off because they're really good. It's not a MoPho photo, but by Neville Drake, taken here at the Briars on the night as well. Okay, this one is the solar eclipse by Dominic Lucarelli, who was actually in Texas, USA. He took a series of photos, and I'm sure he took thousands of them, but this shows the path of the moon across the face of the sun during the course of the eclipse. And it's picked up some really nice shots over there. This one is Comet 12P Pons Brooks by Greg, and it's showing a bit of a time lapse there, and you can actually see the comet actually moving relative to the background stars there as well. This is another one. Who was this by? Peter Lavelle, I think it was. Let's just double check. Peter Lavelle, yes. northern sky time lapse over here. So Peter's got this is his second attempt at AstroMoPho, and he's managed to get a time lapse here of the western sky as Orion is setting, and imaged the relevant stars around there and pointed them out for us. This one was by me, Pons Brooks, taken down at the beach at Seaford. And you can see the comet there, Starlink train shooting tracer fire out, and the comet setting over there. Guido took us for a lap around the sun with a Lego model, which is all... my hand wouldn't have been able to move that fast, but that was pretty impressive. So it's a pretty accurate model from what I saw, and it's all timed and geared to be all quite accurate. Here's one by Sylvie Grandit, as first entry to AstroMoPho. Is that right, Sylvie?
Yeah.
What's wrong with you show that?
Okay.
What's wrong with you show that? What's wrong with you show that?
That was an all-nighter.
So this is the full moon setting in the west, which we see coming up here. And Sylvie, actually, if you go on our Facebook page on the socials, there's actually some really nice music Sylvie's picked on it as well that you can watch. I've sped this up a little bit, but yeah, it's quite a nice time lapse. So well done. Aurora Australis by Dominic from Rye, and you can see the aurora happening there over the hills from his home. So a lot of these videos, a lot of these time lapses aren't just over a clear horizon. They've got some context with hills and trees, which always adds a bit of context as well. Philip Holt got this one. Okay, I'm going to pause this. This is an all sky cam which Philip has got, and what it actually is, it's a hubcam. So polished hubcap, get it and polish up a chrome hubcap so it's nice and shiny, and you set up your camera over it, and you can see the camera there, and it gives you an all sky cam. So you set up your camera on a tripod, point it down at the polished hubcap, and you get an all sky view, 360-degree view of the sky, and he's done this time lapse with that method. The other thing you can see is, which I think, I'm not certain, but this is south, that's north. And I think that is the SAR arc over there. And you can see here from this that the eclipse actually went significantly into the northern sky as well, not just into the south. And I noticed this as well when we were imaging, pointed the camera north, wouldn't expect to see anything, but there's a nice big red glow in the north as well. So it was really a yep.
If you look at the stills from this was moved a bit and moved the stills actually have quite a defined edge to the northern edge to it.
Yep.
And then it seems to back off when you got to the zenith.
Yes.
And I wasn't sure when I looked at it and did it that it's a flaw because of the hubcap itself, or that's actually what you can't see it with your eye.
Yeah, I actually got it as well. When we were imaging, I was doing some test shots in the west. I had my exposure up a bit. One of the exposures showed this arc at the edge of the eclipse, and I thought, oh, that's like an artifact because there was some bright lights underneath it. I thought that was just atmospheric glow from the lights on the ground, but I've seen it in a lot of photos, so yeah, obviously that's what it was. Is that any particular model hubcap you got there?
$10 one from one of the drugstores.
Very good. Greg Walton got this one at the Briars with a fisheye lens. And again, there's that red arc that we've got there in the northern sky as well. So that's quite a wide field of view. any idea about how wide that would be, Greg?
It's 180 degrees. That was more around to these feet, so we figured.
Yeah.
So trying to keep away from the trees.
No, I have taken some license and I've sped some of these up a little bit just to keep them moving. Chris Black got this one as well with the trees in the background. That was a quick one. This one by Lee Hornsby, and this is your first one for AstroMoPho too, isn't it, Lee?
Yeah.
Good job. And this was down at Cape Shank. Cape Shank. Yeah. This one was by me down at Turadum between around about 9 and 10:15. So it starts off quite tame. No, that was someone setting up their equipment in the foreground. In the background, I'm not sure what that was. It could have been. I don't know. I'm going to have to look back at that. Bit of a pan. And these ones here, so these are just with my phone on the night, and that one there is one of my favourite pics, just with people sitting there looking at it with the aurora behind them. This one was by Jamie Pole at Turadum as well, starting at dusk. So as soon as the light went down and aurora became visible. And that's some really nice colour in that. Yeah. Yeah. And yeah. But I think just with that, with the exposure times though, I think if we knew, and the aurora was moving quite quick at some times. No. But if we had taken shorter exposures with higher ISO or shorter exposures anyway, would have been able to get more detail when it all went bang.
The hubcap one, the first part, about 15 seconds, and I had a look at those and thought like they're blurry.
Yeah.
And then I'll go down to 10 and put up to 15 and they then show that sort of ribbon effect.
Yeah, otherwise the motion of it just blurs. And
Lucky when people had occasion to do the film, we wouldn't have had that second opportunity.
yeah, yep. Okay, now these are just some photos. So that was the MoPho Challenge images, and these are just some still photos that have been submitted by members. And these are all on our socials and on our forums if you want to go back and have a look. But yeah, members captured some really terrific photos, and even just with iPhones and that sort of thing, because it was so bright. Okay, the next challenge is the Cosmic Zoo. So anything animal related that you can photograph. This one is the Little Snake Nebula, Dark Nebula in Ophiuchus. But you've got animal constellations, animal nebulas, cat's paw or the lobster, or all sorts of things that are up in the sky at the moment. Even larger constellations that you might be able to image as well. So get out there, get the camera out, start shooting, and yeah, send in your photos. Any questions? All right, thanks very much.
All right, so we have sky for the month for the rest of May and the beginning of June. So the photo for this month was the nice star trail image that Jamie took. I think this was at our telescope learning day or one of those events, maybe? At the PVN, yeah, right. So let's have a look at the solar system first. So this is solar system from the top. And try to find mouse pointer I can't find. So as you can see, all of the planets are kind of on the right side as seen from Earth. That means they're all either very close to the sun or in the morning sky. And we can see that when we fast forward through the month from basically from today until mid-June, not much is going to change there. So both Mercury and Venus will be quite close to the sun, Venus actually behind the sun. And we're getting a bit closer to Mars. So Mars is rising a bit later and later. So it'll come a bit more into the evening sky, but still very early in the morning at the moment, and not really changing very quickly. So it's moving quite slow in the sky at the moment. When we zoom out from the inner solar system, we can see that, oh, that's the wrong one. When we zoom out, we can see that the outer planets are also in the same part of the sky. So Jupiter basically behind the sun, but slowly reappearing. And the only planet that's visible at a reasonable time at the moment is Saturn. The other ones are all morning objects. We'll see that in the other view in a minute. So this is on the 1st of June. So Jupiter is in conjunction with the Sun on the 19th, so just in a few days from now, and then we'll return to the morning sky from mid-June, essentially. Uranus is also in conjunction, or was in conjunction with the Sun, so just behind the Sun from our point of view on the 13th, so just a couple of days ago, and then we'll also return to the morning sky later on. So just at sunset, so around 5 p.m., there's basically nothing to see. If we fast forward a little bit, we can see that the comet 12P Pons-Brooks is still visible there in the western sky. I have another animation of that one a little bit later. And there's another comet in the sky around sunset as well, C2023A3. But other than that, no planets or anything like that. So as you can see, the Milky Way is really prominent during this time of the year. So you can see the Southern Cross and the two pointers in the middle there. And then the rest of the Milky Way towards the east there. So this is around 10 p.m. now. And this is really starting to look like a typical winter sky now. And we can see, when we look at the constellations, that I think they should come up next, hopefully. When we look at the constellation, we can see that Scorpius is actually really high in the sky now, around 10 p.m. at the start of June. So really the dominant constellations in the sky would be Scorpius there, and then of course the Southern Cross in the middle as well. If we fast forward a little bit towards the morning sky, we can see all the planets appear. There's just a few minor planets there at the moment, like Psyche and Ceres. But then after midnight, Saturn rises around 1 a.m. or so, and then Neptune about half an hour later. You can see all the planets lined up there in the morning sky, with the moon there as well. So the moon will have the full moon on the 23rd of May, and then the new moon on the 6th of June, and the next full moon on the 22nd of June. Mars currently rising around 3 a.m. and will very slowly move more towards the evening sky. Saturn rises just after midnight, and the rings are really closing up now, so they're only about 2 degrees at the moment, and I think by March next year they will be. We will look at the rings edge on, so we can now really notice that once Saturn becomes a bit more visible in the next few months. Neptune also rising around midnight. Venus is too close to the Sun to observe. It will be at superior conjunction on the 5th of June when it is behind the Sun. And it would actually be really behind the sun, so there will be an occultation of Venus by the sun on the 4th of June. Now, unfortunately, that is not observable because even you can point a solar scope at the sun, but then you won't see Venus, or you can point a normal scope at the sun, and then you won't see anything afterwards because you're blind. So that's not a very interesting. But NASA will actually point some space-based telescopes at this event, so we might actually get something from that. And then Mercury will also be in superior conjunction on the 15th of June. So it's still visible in the sky at the moment, but it will kind of disappear behind the sun then. Right, and I think sunrise will be around 7:30 or so at the start of June.
Where's Pluto?
I don't know where Pluto is. It's not a planet. So I should put it in. You're right. I think
It's a dog.
that's a very good point. Right, Pluto is a dog. That's a good target. I think Pluto is visible, actually. Yeah, I think Pluto could be a target.
It's near Sagittarius.
Near Sagittarius.
He
Okay.
was there last year too. Right?
Yeah, it's yeah, and you can see there Jupiter, Mercury, and Venus very close to the sun there after sunrise. So the apparent sizes of the planets are not very interesting because most of them are not really visible, but that's the sizes that you would see. The only thing maybe that's interesting here is, as you can see with Saturn, that the rings are almost closed now, right? So we're almost looking edge on. It's only a 2-degree angle, and that'll get even less over the course of the next year. Right, looking at comets. So Pons-Brooks is still visible. I mean, we just saw the nice images from last weekend. It's setting around 8 p.m., but it will now start to fade towards magnitude 9 or so. So probably now is the opportunity to actually take some images or observe it because it's reasonably high and still bright enough. There's a couple of other comets, 13P Orbis, but it's setting just after sunset, so probably not the best target. And then 23A3 Tsukkin-chan Atlas in Virgo and Leo, and it sets just before dawn, but it's magnitude 11, so it's relatively faint. I've got the Pons-Brooks animation here, so you can see where it is. So that's starting today, and then one tick is 1 day, basically. So you can see that it is still getting a bit higher in the sky. So you can see that it will move towards Sirius there. So it will get a bit higher in the sky over the next couple of weeks or so, but also fade to magnitude 9 or so. Not much going on in terms of meteor showers. The Eta Aquariids have peaked, but they're still technically going at the moment until the 28th, so just for another week or so. And other than that, there's no other meteor showers at the moment, and that's pretty much all. The sources, as always, Stellarium and NASA Eyes on the Solar System, and then the Astronomy 2024 yearbook. Any questions?
Okay, now we'll come to the main video for this evening on space storms in the upper atmosphere and the ionosphere. It'll be given by Dr. Stan Solomon here from Boulder, Colorado, from the National Center for Atmospheric Research in the USA. And this was a public lecture from a few years ago, so there are actually surprisingly few talks online that I could find about the aurora. So I was actually quite surprised at how difficult it was to find something more than just a picture show.
So I'm going to discuss space weather, meaning storms and also quiet periods that occur in the upper atmosphere and ionosphere of the Earth. And when we use this term space weather, it's really an analogy. The storms in this very extended region of the Earth's atmosphere are very different They're not exactly the same thing as tropospheric storms, but their variability, sometimes dynamical variability, sometimes dramatic variability that occurs in the system, and so we have given the field that name in order to make it a little more accessible, but it is in a way a branch of meteorology. It's just very, very different because you have electromagnetism involved, and at the same time you don't have some of the complicating factors of the lower atmosphere, like water, for instance. So I'm going to talk about the main source, not the only source, but the main source of space weather, which is variability in the sun and the solar wind. Say a few words about the magnetosphere, ionosphere interactions. I hope I don't have to introduce some of these terms. Magnetosphere is the extended region around near Earth space. It's controlled by the Earth's magnetic field. Say a few words about the impacts of some of these variability, why we might care about things that occur from space weather. Give an overview of the thermosphere and ionosphere system, really the atmosphere ionosphere system, because the thermosphere is part of the atmosphere. It's the very upper part of the Earth's atmosphere. And then talk about auroral forms, the global electric circuit, how that leads to these geospace storms that occur in the magnetosphere ionosphere system, but to a great extent manifest themselves in the ionosphere. So I'm going to start by showing this photograph or set of superposed photographs, just because I like it so much. It's fairly recent. This is a image by Miloslav Gutmuller from taken during the Great American Eclipse of 2017, and by use of multiple images and image enhancement and some very sophisticated techniques, he has managed to really bring out the features in the solar corona that tell you the great extent to which the corona is controlled by solar magnetism. Magnetism is going to be a constant theme of this talk. You can visualize through the illumination of these field lines the morphology of the solar magnetic field, as if there were a bar magnet inside of it, and then you can see all this structure due to departures of that magnetic field from just a plain magnetic field to one that's controlled by active regions on the sun. The corona and the magnetic field that's embedded within it stretches far out into space. In fact, you could consider the corona of the sun as you can consider the Earth as being inside the corona of the sun, even because the solar wind constantly outflowing carries electrons from the sun, all electrons and protons, and in fact other ions, all the way to Earth. And the variability in all of those particles and fields are ultimately what's driving most of variability in the thermosphere ionosphere system. Not all of it. Some of it is coming actually from the atmosphere below, from the troposphere and ground atmosphere interactions. But those changes are somewhat less dramatic, and we won't be able to get to that aspect of space weather today. So when we think of solar magnetism, we speak of active regions, which are places where the magnetic field is distorted and concentrated into local, you might even call them hotspots. And these are associated with sunspots. They're not quite the same thing as sunspots, but they're different manifestations of the same process, which is variability in the solar magnetic field. So in order to understand how variable that is, we can look at a longer term record of solar magnetism as manifested in this case by the sunspots before we had ultraviolet images. This is an image in the ultraviolet. You couldn't see this in the plain visible light of the sun, but by normal visible wavelength techniques, you can track sunspots and track for centuries really, and give us a record of how variable the sun is. There's approximately 11-year periodicity to that variability. That's still not fully understood why that the solar activity should be so regular in the timing of its variability, and yet so different, both with regard to the active times and the quiet times. But also, each active time is different in intensity, and we now understand that the quiet times as well are not all the same. It's not as if the sun constantly returns to its same state. So this plot's about a cycle old. This last cycle, since 2012 or so, 2010 or so, has been a very modest cycle. It's just come to an end, and the next solar cycle is now picking up, and hopefully we'll get some interesting variability out of that. It's interesting solar phenomenon that will drive terrestrial phenomena. Hopefully not too interesting. We don't want any catastrophic. Here's the same type of representation, but in a very different way. In recent years, we're able to track the solar cycle in X-rays and extreme ultraviolet. Here is in X-rays from essentially one cycle from maximum down to minimum and back up to maximum. These are one image per year, basically. It's representative of that year. And you can see that as we get down to solar minimum, all of this interesting structure dies away. That doesn't mean that there aren't still events going on in the sun that are manifesting themselves at Earth, in the upper atmosphere and ionosphere of the Earth, but it's much less dramatic, and obviously when something big like this goes off, the X-rays. Now, when we see events on the sun, people often speak of solar flares, and one thing you may have heard is that auroral phenomenon, space weather, changes in the ionosphere, that this is all driven by solar flares. And that's half true. Solar flares do impact the outer regions of the Earth atmosphere and ionosphere, but they're really just the photon manifestation of that phenomenon. They, of course, because they're photons, they get to Earth very rapidly. They do cause ionization and so forth. They produce their own electromagnetic radiation over all wavelengths, and can be very dramatic, but they don't carry as much energy as the coronal mass ejections, to which they are closely related. You could say they're different manifestations of the same solar process. Wanted to run this one. This is a image sequence from a NASA satellite of a solar flare. Sorry. There it goes. And you can see all of this hot plasma, meaning mixture of electrons and protons and maybe heavy ions shooting out from the sun. And then they're both emitting in the very short wavelength, the energetic X-rays and ultraviolet, and also they're scattering solar light, sunlight, off of the the electrons that are carried near the sun. Here's one of those coronal mass ejections. Different in the sense that you actually have energetic particles that are still very small light particles, low in density, but much higher than the solar flares, and in terms of their total energy. And you can see one here. Look at this area here. You'll see it shooting off to the right. And when one of those impacts the Earth, see two of them actually, one up here, one down here, one up here. When one of those impacts the Earth, and of course in this case they're mostly going off to the side, but when you get one coming right at you, that is when you have the most dramatic consequences for the extended atmosphere, ionosphere, and magnetosphere system. So that's illustrated by this NASA sort of cartoon representation of space weather processes. This is what happens when a CME comes right at you. If you could see that, you would see a explosion of light directed towards the Earth and entrained in the solar wind. Now we're looking at it from the side. That impacts the magnetic field of the Earth, causing events to occur in the tail of the magnetosphere, the so-called magnetotail, and energization to occur that interacts ultimately with the Earth's atmosphere and ionosphere. That all went by very fast, so let me see if I can catch a few highlights here. This is what the magnetosphere of the Earth roughly looks like if you could see the field lines that define the morphology of the magnetosphere. It starts as a regular magnetic field, a dipole-shaped magnetic field, but because it's embedded in the solar wind, it gets stretched down in this long magnetotail region. And then at the front end, you form a shock wave because the solar wind, consisting of electrons and protons flowing rapidly out from the sun, more rapidly during one of these big ejections, but it's there all the time. And because it's supersonic, in this, again, this is by analogy with hydrodynamic processes, just as we can speak of a hydrodynamic flow or something moving within the atmosphere or for that matter, the ocean. If it's moving faster than the wave propagation speed, we speak of that as supersonic or hypersonic. And the solar wind is the same way, except the waves that we're speaking of are waves within the magnetized plasma. And so it's and since there's a mathematical analogy between magnetized plasma motions and hydrodynamics, atmospheric or fluid motions, we pursue that analogy by saying, well, that's a shock wave. And then what happens in the magnetotail of the Earth is you get reconnection between these magnetic field lines, which are normally distended out into the tail. And this energizes plasma and causes it to flow down the field lines, where those field lines connect to the polar regions of the Earth, and consequently you get emissions of light coming from the particles impacting the upper atmosphere that occur in the vicinity of the magnetic poles of the Earth. So that was all a lot to take in from a simple cartoon, but it's a nice illustration. Here's more of a schematic. Again, it's a simplified sort of imaginary diagram of the structure of the magnetosphere as it connects to the Earth's ionosphere and upper atmosphere. You have the solar wind coming in because it's supersonic. You get a bow shock, just as you would in front of a supersonic jet plane. This tends to deflect the solar plasma. And in this sense, the magnetic field of the Earth, think of it as almost protecting us changes in dramatic changes in the solar environment. But at the same time, this structure where the magnetic field here near the poles connects way down to the extended tail of the magnetosphere. Events that occur in the magnetotail map themselves into the polar regions of the Earth's ionosphere and causes disruptions of the electric field within this ionosphere that extend over the entire globe. I'll show sort of schematics or illustrations of this a couple of times. Try to soak it in. It's not a simple process, but this is the big picture of how the sun and the solar wind are interacting with the Earth's magnetosphere. So the idea that the sun is driving these things, but indirectly, the flare effects, although they exist, are smaller, and the solar wind effects can be dramatic, but they're modulated or translated by the Earth's magnetosphere. Here's a model of that process. The colors are the density of electrons flowing in from the solar wind. We have a little compass here indicating which direction the solar magnetic field is. I mentioned before that the magnetic field, which is embedded in the corona, spreads out through the entire solar system, not just near the sun. So we're embedded in both our own magnetic field and the solar magnetic field, which is sometimes referred to as IMF, interplanetary magnetic field. And the interaction between those two things is what causes a lot of the dynamics of the magnetosphere that imprints itself onto the ionosphere atmosphere system. You see that little shock front moving across as a solar coronal mass ejection impacted the Earth's magnetosphere. So electrons and protons, electrons are doing most of the work here, that are energized in the magnetosphere can then flow along magnetic field lines. This little representation here shows that they're actually spiraling along the field lines. I'll show another representation of that. They're constrained to move by the electromagnetic forces constrain them to constantly move back towards their field line. So if they have some motion in a particular direction, they are attempting to go in that direction, but they're constantly connected to the field line because they feel the electromagnetic force. So that then, as they flow into the upper atmosphere and ionosphere of the Earth, very high altitude, they collide with things. And when they collide with things, they excite them, and they dissociate them, and especially they ionize them. When the excitation processes and some of the dissociation processes cause the atoms and molecules in the Earth's atmosphere to emit light, i.e. the aurora, and the ionization processes contribute to the density of the ionosphere and causes additional changes to the ionospheric electric circuit, which causes a lot of space weather. And you can almost imagine that, if you look at this picture of the aurora, there's currents flowing down into the Earth's ionosphere from the magnetosphere, but they're also flowing along these conduits that are caused by the enhanced ionization. So just say a few words about why we might care about these things. We'd like to say, well, we are living in a technological society and space weather affects us all. Now, most of the important systems have ways to mitigate changes in the ionosphere and changes in the magnetic field structure near the Earth's of near Earth geospace, as we call it. But you can still cause disruptions in navigation systems such as GPS. Satellite operations, meaning both technical things that happen when particles hit satellites, but also navigation in near Earth space. I'll say a few words about that in just a second. Human spaceflight, of course, because humans are vulnerable to radiation of several different types. Communications especially, most of these effects have to do with passing radio waves through the ionosphere or bouncing radio waves off the ionosphere. And so consequently, large scale and micro scale, all scales really, of perturbations in the ionosphere can affect radio communications or other uses to which radio waves are put, such as GPS navigation. Aircraft operations, same thing. Navigation is of course a concern, and any kind of radio blackouts or polar disruptions are of concern to transportation, because aircraft don't like to be out of touch with their with the ground. Power grid operations is a little different. The perturbations in the electromagnetism near the Earth's surface are very small, but when you have a very, very long antenna, you can concentrate small fluctuations, and long power lines can serve as such antennas, and consequently, power transformers can be vulnerable to space weather events. Most of those are impacted through design. When your power goes out, you usually look to a windstorm or a hailstorm or something. The first thing you think of isn't usually that a space weather event has knocked out your power. Nevertheless, it has been known to happen. It has to be guarded against, and for reasons that are still obscure to me, it is a demonstrable fact that the spot market for power cost, which is very dynamic, moves on very short timescales, does respond to geomagnetic indices, whether by the law of expectations or superstition. It's hard to say why, but it's been demonstrated that people who care about power grids care about space weather. So let me say something about satellite operations. Near Earth space is getting very full, even a little farther from the Earth. This is a graphic where every point, every spot on this graphic represents a satellite or a piece of something in space. Most of it is debris, as I say. Most of it is so-called space junk, remnants of other satellites, things that flew off of satellites when they blew up for one reason or another, or collided with something else, causing an explosion. And as we populate space, especially closer to the surface of the Earth, with more stuff, we cause more debris and more risk of collision. And so somebody put together this animation for NASA. I think it's sort of spectacular. This outer belt here, this is the geostationary belt. This is where the communications satellites, TV stations are, and so forth, because they have the property that they're over a stationary point on Earth. And if you rotate and come in from the side, you can see that belt. And then there's many objects in sort of middle Earth orbit, where still it's not terribly highly populated, but as you come in to near-Earth space, there's an incredible density of objects orbiting the surface of the Earth. Now, of course, it's not as bad as it looks on this plot, because each dot is much bigger than a satellite to scale. But the risk of collision in close here is getting high and growing. Now, at much lower altitude, you have a gap, because once things get low, they encounter the atmosphere much more rapidly, and orbits decay and the satellites burn up. But down to about 300 or 400 kilometers, you have a belt of very high density of functioning satellites. A lot of these are functioning satellites, but most of it is just debris. Consequently, the functioning satellites are not enthralled of the prospects of having to fly through this debris field constantly. And now there is a prospect of dramatically increasing the population of these near-Earth orbiting objects due to commercial communications operations. And so the changes in those orbits, which occurs when they encounter the neutral atmosphere, even at very high altitude. Now, way out here, geostationary, there's not enough atmosphere to change their orbit. But in close here, as the atmosphere of the Earth changes, the orbits of our functioning satellites change, and as well as the space debris. And all of it has to be tracked. There's often little you can do about avoiding a collision, but it's nice to know about near misses, which are becoming quite common. So that's one of the rationales for trying to understand not just the ionosphere, but the neutral part of the Earth's upper atmosphere, into which the ionosphere is embedded. So that's one of the rationale for wanting to understand that. The other rationale being to understand, another rationale being to understand the ionosphere itself. So I mentioned that the ionosphere is embedded in the thermosphere. There's one factoid takeaway that, if you didn't know it before, to take from this overview, this very, very high level overview, it would be that the ionosphere, although it's largely referred to as the ionosphere because it was discovered early on through its ability to reflect and refract radio waves, is still mostly neutral. And it exists in the extended atmosphere of the Earth. We define the atmosphere of the Earth by its temperature gradient, troposphere, negative temperature gradient, getting colder as you go up in altitude. Stratosphere has a positive temperature gradient, primarily due to heating from ozone, absorption of sunlight by ozone. Cools down again as you go up in altitude in this mesosphere region, which has its own peculiar weather. And then if we get into the thermosphere, not only does it dramatically heat, but there's a big difference between solar minimum and solar maximum. Reason for that is that this is a region that's absorbing all of that extreme ultraviolet radiation from the sun and X-rays. And though that region of the sun spectrum is very variable, it also causes ionization. Ionization happens with large cross sections. It's highly probable compared to some of the processes that happen lower down. And so even though the density is very low out here in the thermosphere, it's still quite likely that a solar photon of the extreme ultraviolet hits something, and when it does, it ionizes it in general. Here is a plot of the same region of density. Note we're going over 12 orders of magnitude on a logarithmic scale. So this tells you two things. The atmosphere is dropping off in density in an exponential fashion. It's a straight line on a log plot, if that helps explain it to you. And it's dropping off very rapidly. Below 100 kilometers, there's a fundamental difference between I should say a fundamental change that occurs at around 100 kilometers. The atmosphere changes from fully mixed to diffusively separated. What that means is that down here where we live, there's enough turbulence that that everything gets mixed up, and the gases don't care how much they weigh. They're going to follow this drop off, this exponential or logarithmic drop off, all about the same rate. So N2, molecular nitrogen, and O2, atomic molecular oxygen, and other gases that, if they're not chemically active, like say ozone, they are all mixed together, and they have parallel lines on this logarithmic plot, meaning that their ratios are fairly constant. You get to 100 kilometers, a couple of things change. One is that all the O2 starts turning into O. That is, the molecular oxygen starts turning into atomic oxygen because it's being impacted by those photons, those energetic photons from the sun. It's getting dissociated and ionized, broken apart. And the other thing that happens is that because the molecular diffusion now takes over as a main process, and that depends on how much the individual gas weighs or what its mass is. And so what happens is the lighter stuff, like atomic oxygen, starts following its own scale height. That is to say, it diffuses upward into space more rapidly and drops off more slowly, whereas the heavier stuff, like say molecular nitrogen, or especially molecular oxygen, drops off much more rapidly. So when you get up into the ionosphere here, we'll get to that in a minute, but as you get into the upper thermosphere, the atomic oxygen takes over, and eventually the upper atmosphere, the upper part of the thermosphere, becomes predominantly atomic oxygen, whereas down here where we are, it was predominantly molecular nitrogen, with, fortunately for us, a little bit of molecular oxygen. So into that atmosphere, we pour all of this electromagnetic radiation, so sunlight. Down here, the peak of the black body spectrum of the sunlight, it's around 500 nanometers. This is the visible region, and consequently I've colored it yellow. It's not very variable. What I've done here is I've put a high solar activity spectrum in red behind the yellow, the low solar activity spectrum in yellow. So the variability appears as this red fringe. And so in the ultraviolet, you can see there's a very small amount of variability. As you get into the extreme ultraviolet, this is the part that causes ionization. You get a lot of variability, a factor of 2 between solar minimum and solar maximum. And that becomes as much as an order of magnitude in the X-ray region. So that explains why the thermosphere temperatures and densities vary so much with solar activity. They're being controlled by this very shortwave extreme ultraviolet and X-ray radiation that's is depositing its energy way up high here, around 100 to 200 kilometers and higher, whereas the less variable regular ultraviolet is coming down here. This is not so much ionizing as dissociating parts of the middle atmosphere, and down here it's being absorbed by ozone, which causes stratospheric heating. And then as we get from the ultraviolet to the visible region, it reaches all the way to the ground. And but by the time we get out here, the solar variability is very small, less than 0.1%. So not only does that cause the temperature of the thermosphere to vary dramatically, but it causes the density of the ionosphere to vary dramatically, because the ionosphere is being made by the absorption of all that extreme ultraviolet radiation. And so at solar maximum, we have an ionosphere that is much, peaks around up here at around 300 kilometers. It's much more dense. That is, they say there's more ions and electrons than at solar minimum. now as you go from day to night, you also have a big change. And that's because the ions up here, primarily O+, atomic oxygen ion, are fairly long-lived, more than a day, but they don't last forever. So once the sun goes down at nighttime, they largely diminish the density as they diffuse back down into the lower ionosphere and as they recombine. In the lower ionosphere, the change is much smaller between solar max and solar min, but it's much larger from day to night. And that's because here in the lower ionosphere, you have a lot of molecules, a lot of stuff to react with, a lot of more density, and the lifetime of the ions is much smaller. So once the sun goes down, they largely go away, and the ionosphere becomes dominated by this so-called F region at high altitude. The F region may look like a conventional Chapman function, but it's really not. It's a balance between the diffusive properties of the ions and the recombination that occurs at lower altitude. And this code, DEF, this is dates back to the dawn of the discovery of the ionosphere. The E region was discovered first and named the electrical region, and then well, what's above the E region? Turns out there's a lot of ionosphere above the E region. What are you going to call it? The F region. And so you will, because this region is so important to ionosphere electrodynamics, often we just refer to it as the ionosphere and say, oh yes, up in the ionosphere around 300 kilometers. But even though there's a lot of ions up here, 1 million per cubic centimeter at its peak and more, they're not nearly as numerous as the neutrals. Neutrals still control what's going on to a great degree. The ions have a lot more energy and a lot more motion, but there's a lot more neutrals, 1,000 times more neutrals, even here at the peak of the ionosphere. And then of course, it only gets more neutral as you go lower, the ions get lower and the neutrals get higher. So that's why we really refer to thermosphere ionosphere system or the thermosphere ionosphere as a region. It's still predominantly as a thermosphere, but that's not a term that is as familiar to most people as the ionosphere. And here again is this F region, E region. There's a little bump here at the E region. It's that's another one of these historical things. People used to speak of layers because when you're bouncing a radio wave off it looks like a layer, but it's really a pretty broad layer, especially in the F region. It's more of a region than a layer, but you hear people talk about layers a lot. So because the F region has long-lived ions, they can spread out and get entrained in the electrodynamics of the Earth system. Because the Earth's magnetic field has a strong interaction with these electrodynamical terms, you get two big belts of ionization in the F region, one on each side of the magnetic equator, and those regions are subject to instabilities and dynamical plasma processes that respond a lot to the Earth's lower atmosphere and form another type of ionospheric variability. But for the type of space weather that's solar driven that we're mostly speaking about today, it starts in the polar regions. Here's another ultraviolet image of the aurora. Again, if you were to see this in the visible, it would be super bright over here in the illuminated part. This is the part of the atmosphere that's illuminated by the sun, and you get certain emission processes in the ultraviolet, but the aurora can compete with those And so this is a good visualization of where the aurora is, but it's very smeared out. This is a sort of a discovery image from several decades ago. We first were able to make a comprehensive image of the aurora from fairly high altitude. And so it's it took 12 minutes to make this image, and it's kind of smeared out both spatially and temporally. From the space shuttle, we were able to get dramatic images from low Earth orbit. You can see all this structure that's actually occurring in the aurora, this interesting color morphology with the red parts of the visible spectrum at high altitude and this blue-green part at lower altitude. The hard limb of the Earth, the solid Earth, starts all the way down here. This is where the aurora is depositing most of its energy, up around 100 kilometers. Here's a dramatic one from the space station. This is time-lapse photography. It's sped up by about a factor of 10. The aurora is not moving around that fast, and nor is the space station, but it nicely captures just how dynamic these currents are that are connecting the magnetosphere and the ionosphere and are controlling and training the aurora, being the optical manifestation, in this case, actual visible light radiation that's being generated by the impact of all those energetic particles that are following along with the current system. So here's just to emphasize this high altitude red, medium altitude greenish blue. This is a photo. This is a photo I took in Alaska. Showing a moderate auroral activity. You can almost see the curvature of the auroral lobe as it stretches across the horizon away from you. I'll show a few other images. This is one of the last ones that I actually took myself. Oh, let's see. Let's back a bit. Let's just recapitulate what's going on here. We're getting optical emissions. They're being generated by electron impact processes that occur when reconnection occurs with the magnetic tail of the Earth and causes charged particles, in this case primarily electrons, to flow back down towards the Earth. These field lines connect in the polar regions. Consequently, we get the polar aurora, sometimes aurora polaris. They're moving along field lines because they're constrained to travel along spiral trajectories, and consequently the field line morphology controls the electrical field morphology and the auroral morphology. Here's another one of these nice NASA cartoon animations that sort of help you visualize that. Imagine that these were flux tubes spewing charged particles from the magnetosphere down into the atmosphere. Here they go. These are the electrons moving along their spiral trajectories and dumping out into the vacuum of near Earth space until they encounter the atmosphere. Once they encounter the atmosphere, they start hitting things. If they hit one of these gray atomic oxygen atoms, they might glow red if they're at high altitude. If they're at lower altitude, they are more likely to glow green, although it's coming from the same atomic oxygen, or they might hit a molecular nitrogen, one of these two-part blue things, and emit light in the blue and at other wavelengths. The auroral spectrum is much more complex than that, but that's a nice way to think about it and explains the basic morphology of the multiple colors that make up the aurora. There's atomic physics reasons why the red tends to occur at high altitude, green at lower altitude. has to do with the long lifetime of the red emissions, the so-called O in the singlet D metastable excited state. Because it has a long lifetime, it's unlikely to emit at low altitude because it will encounter some molecular atom and become collisionally deactivated before it has a chance to emit. How far down into the atmosphere do the electrons penetrate? Well, it depends on how energetic they are. The more energetic they are, the deeper they go. And that, therefore, controls some of the phenomenology of the auroral emissions. They can get even below 100 kilometers into that mixed region of the Earth's upper atmosphere, but most of the auroral forms are coming down in here, 100, 120 kilometers, except for the very soft electrons, which preferentially deposit at somewhat higher altitude. And again, these softer ones can emit even up above 200 kilometers. When they encounter the neutral atmosphere, again, here's one of these plots with the neutral atmosphere and the ionosphere on the same axes, dashed lines for the neutrals, solid lines for the ions, the black solid line for the electron density. When the aurora comes in, you get an enhancement of electron density in the 100 to 200 kilometer region. And that is accompanied by the optical emissions, but also enables the currents to flow, the magnetic currents to flow through the ionosphere, because you have more conductivity here in the ionosphere because you have more electrons and ions. So just an overview, the aurora is usually pretty green in appearance because that green atomic oxygen emission is pretty dominant. It takes a fair amount of energy to be able to separate out this sort of green-blue from the red at high altitude, but you can see that from the ground easier with photography. Here's some nice images from Alaska taken by my colleague Dave Fritz during a really major storm. This, you even get the red at lower altitude. This is a different emission, but it's another nitrogen emission that happens when aurora gets down to very low altitude. As the geomagnetic storm breaks up, you have all the structure occurs in the emission forms and presumably in the electric fields as well. This is looking straight up one of these features, the so-called aurora corona. You can see the convergence of the forms to the zenith as you look up. That's to say the magnetic zenith. As you look up the field line toward the pole, there's a lot of vorticity in those features. This is another one I took from Greenland. A fairly long time exposure, trying to capture just how much this feature is swirling around as you look up along this field line. You could even call it a flex tube. May contain some clue as to the nature of the reconnection mechanisms. This is a nice evocative picture because this is from another one from the NASA archives coming out of the space shuttle era. Captures nicely the idea that the energy source for the aurora is in fact the sun, but this is not the sun, of course, it's the moon. If it were the sun, everything would be too bright for us to see anything. And here finally is one of my own. You may recognize the locale if you're local. This is the Boulder Flatirons in the background. Deciduous trees. It's even November in this photo. And this is very overexposed, but you can see the NCAR Mesa Lab in the foreground, partly illuminated. And at the Mesa Lab, if you ever get to go back into it again, you may find this photo in a few different places. So just to talk a little bit about our efforts at NCAR to capture all this, here's an animation from a slightly older model, a little lower resolution, but capturing the effect of a storm as it impacts the thermosphere ionosphere system, both the lower ionosphere, where you have the aurora very visible in basically ion density here. That changes the neutral temperature all throughout the thermosphere, and that changes the composition of the thermosphere. Remember I said it was mostly atomic oxygen and molecular nitrogen. If you look at the ratio of those things, that's quite variable, especially in response to these storms. And the combination of temperature and composition cause the electron density in the F region to also be quite variable as the storm progresses. And this is too much information at once, but if you wanted to see that simultaneously instead of sequentially, it would look like this, with the aurora driving everything and the neutral atmosphere impacting the electron density in the ionosphere, just as the auroral electrodynamics also impact the ionosphere. So in order to understand that, we need higher resolution models, we need better time resolution, we need more complexity and more realistic magnetosphere physics. And that's all attempted by a new partnership led by colleagues, Johns Hopkins University Applied Physics Lab. It's a study for a proposed NASA center called the Drive Center, typical acronym. And one of our main goals is to construct improved coupled models of this magnetosphere, ionosphere, atmosphere system. I'll just show some previews from what we're trying to accomplish. This is also a animation of the ionospheric response to a geomagnetic storm, but at considerably more resolution. And looking especially at that equatorial feature, it's there all the time, but when the storm hits, which is about now, it becomes completely dynamic, changes its morphology entirely. You can see all the action going on at high latitudes. And you can see that although the magnetic field near the equator is still in charge, and we're going back to its sort of baseline configuration with one arc on each side of the magnetic equator, which is going down through here. The storm has had a lot to say about reconfiguring the entire ionospheric system. Just show this one quickly, wrap this up. The neutral atmosphere is also very dynamic in response to one of these storms. This is a polar view of the north and south poles of waves in the neutral density coming out of the auroral region in response to day-to-day variability, which you're seeing now, and a storm, which is about to start. And these plots and the dots moving through the colors are data of density from a couple of satellites, just to show that we can capture most of the variability we see in the density, but we don't capture it perfectly, not yet, maybe not ever, but we can capture some of these peaks, these spikes in density as the satellites move through these wave-like features we call traveling atmospheric disturbances. Here comes some big ones. See us didn't do too well on that one, but this one here, I think we capture density change very nicely. So this is pretty high resolution stuff. This is using resolution comparable to the big new planet models. So I'm going to wrap this up here. I'm just going to anticipate a question just in case. I've written it down just in case you, this is something you want to, not an uncommon question. Where can you see the aurora? Well, you may have a better chance that we get more solar activity. And what you really need is to see space weather is good weather. A fairly dark sky, doesn't have to be perfectly dark. The aurora is always there, usually at very high magnetic latitude. If you're not near a magnetic pole, you want some activity so that this expansion of the auroral oval that brings it down to lower latitude, lower magnetic latitude, can help you bring it within your sight range. Equinoxes are a little better than the solstice, but that's not a very, that's just a statistical variation. Forecasting is in its infancy, but there is a commercial and government websites that you can go to try to anticipate when there might be some auroral activity. And consequently, you can position yourself in a place to see it. There's even apps. And here are some examples of graphics from the NOAA Space Weather Prediction Center and other locations of international nature. So there's information out there with a little interpretation about all this having to do with solar wind measurements. You can try to figure out when might be a good time to see the aurora, or you can exploit geographic serendipity if you ever are in, for instance, Alaska, which is reasonably well situated geomagnetically for this type of observation. So I will wrap this up here. And be glad to field any questions.
Great. Well, thank you so much, Stan. That was wonderful. It was very insightful on kind of learning about what is one type of space storms caused by specifically solar-driven space storms today. And one of the biggest things I learned was that solar flares and coronal mass ejections are different. And there's a lot more photons that are passing through space, like from the coronal mass ejection. So it's going to be really interesting to see how the sun keeps evolving in time. And yeah, so we do have a few questions on Slido. So I can ask Dan, would you be able to post up the questions? And then Stan, you can just go through the questions as they were asked. And I'll just let you handle those.
How vulnerable is our electrical grid to these coronal mass ejections? When was the last time the Earth took a direct hit? We got some pretty good hits in 2013, 2014, and then most recently 2017. As I mentioned, this last solar cycle, totally different subject, but this last solar cycle was not particularly strong. We didn't get a lot of big storms. We didn't get a lot of radiation, of variability in the solar output in the extreme ultraviolet. But this one that's just starting now may be stronger. There used to be a fair amount of skepticism about impacts on electrical power grids. I remember one of the NASA administrators a while ago said, well, somebody please show me a picture of an electrical transformer that's been knocked out by a space weather storm. But then people produced them. It's not a common or frequent event. But as I said, I believe, with a total lack of expertise in this area, but I believe that they are finding ways to engineer around this type of problem, which is, of course, the answer to a lot of space weather problems is to a great degree, you want to build systems that are robust enough to withstand space weather events, which of course leads you to the question, well, how bad can it get? So, I would say that serious power outages, transformer damage is not a common thing, at least not now, but it is certainly possible. And one of the things that's been pointed out is that for these very large transformers, which maybe have some vulnerability, replacement can be a very large scale and time consuming task. And so, and you can't just go, you can't buy one of these giant transformers on Amazon and just have it delivered the next day. It can be consequential if one of these things goes. So and also there's a lot of concern about analogous processes such as electromagnetic pulses that can be human induced. That's not an area where I have any expertise either, but I know that there's a lot of interest in certain segments in that subject.
Great, thank you so much. And it takes a lot of engineering to make sure to work with you to be able to keep our infrastructure.
Yeah, to some degree, the space science side of this it can be considered to be putting upper limits on things. We think of this an analogy with, by using the word space weather, we think, well, that must be analogous to tropospheric weather. And well, what do you want to do with tropospheric weather? Well, of course, you want to forecast it. But a forecast will only get you so far. Okay, so why do aurora formed at different altitudes display different colors? I started to touch on that, but it's really a whole much longer story. It's due to two primary things. One is the change in composition, that is the molecules and atoms that make up the upper atmosphere, changing over from atomic oxygen at high altitude to mostly molecular nitrogen, and also molecular oxygen at lower altitude. If you can bear to think of 100 kilometers as being low altitude, and who doesn't, then you get a different mixture of colors as things change with altitude. Also, the storms themselves change the composition mix. And then on top of that, you get basic atomic physics. Things that are long-lived, meaning have long lifetimes against radiation, preferentially emit at high altitude, because when they get down to lower altitude, before they have a chance to emit, they get what we call collisionally deactivated. They undergo collisional deactivation. They run into something else. And that collision takes away the extra energy of excitation before it can have a chance to emit. So you get a complex interplay of all these different things, and that explains the fact that there is so much variability in the auroral spectrum, but it still means that it's a daunting task to take a driving mechanism and reconstruct what the auroral spectrum might be, or vice versa, to look at an auroral spectrum and figure out what's going on.
Awesome. Thank you so much. Dan, can we see what the next question is?
What's the scientific rationale for high geomagnetic activity near the equinoxes? Oh, that's an even longer story and maybe a little bit controversial. It's called the Russell-McPherson effect, because Chris Russell and Bob McPherson first identified it. If you look statistically at indices of geomagnetic activity, you will see a slight preference for the equinoxes, and that has to do with the way that the theory is that has to do with the way that the Earth's magnetic field lines up with the solar magnetic field, the so-called interplanetary magnetic field, and And when during the equinoxes you have a more favorable configuration for magnetic reconnection, it doesn't affect the likelihood that there'll be a big solar storm, right? If there's a big solar storm, a big coronal mass ejection, that's not going to care where the Earth is in its orbit, whether it's equinox or solstice. But there's a lot of lower level activity that's going on all the time that can be slightly amplified by this alignment between the solar magnetic field and the Earth's magnetic field. And of course, that alignment also can affect the way that a major solar storm, coronal mass ejection, can interact with the Earth, but probably has less of an effect on its absolute magnitude.
Great, thank you so much. That is like a whole research in itself. Dan, can you please share with us what is the next question that we might have?
Do other particles, protons, atomic, and nuclei from a CME also contribute to the aurora? And if yes, in what way? They contribute to impacts on the Earth's atmosphere. They don't tend to make as much in the way of visible manifestation or ultraviolet, of light emitted from the aurora. They tend to be much more spread out than these highly structured forms that come basically from the magnetosphere of the Earth. But there's so many aspects of solar activity. I don't have time to touch on all of them. One phenomenon is known as solar proton events. And these are in fact particles from the sun. I tried to drive a couple of messages. The ionosphere is mostly neutral. Aurora isn't just particles from the sun, it's really more like particles from the magnetosphere. But solar proton events really are particles from the sun that are energetic enough to penetrate the magnetosphere. They tend to deposit their energy at even lower altitudes, where they contribute to the chemistry of the middle atmosphere, and in a minor way, but they can impact the chemical processes through the same sort of mechanisms of dissociating and even ionizing things. But in terms, when we say aurora, we think of the visible manifestations and the stuff that you could see either from space or from the ground. They don't tend to contribute as much to that aspect of the phenomenon. They're harder to see a solar proton event unless you have specialized instruments in space.
Wow, there's just so much going on up there. It's crazy because I just kind of worry about what's happening in my house.
Yeah, well, I guess so people get caught up in this stuff too much sometimes. I mean, it's not like the aurora is coming into your television set and electrocuting everybody in your house. It has more to do with currents flowing either at high altitude or through very long conductors.
Awesome, thank you. And then we do have a final question, Dan, if you can post it up. And it asks more so, what's your day like at work? And I kind of wonder if this can be kind of like, what kind of work are you doing? Are you doing the computational aspect of the research?
Is this a question for the last 8 months or so, or a more generic career-based question?
I think it might be the career-based question.
I think so. And of course, since most of my work is done on computers, we have the great good fortune of being able to continue working during the stay-at-home environment. Although, like everybody, it requires a lot of reorientation in a lot of different ways. But that aside, my daily work is largely on contributing to my areas of expertise as they pertain to this large-scale model development to which I alluded, and in utilizing measurements primarily from space-based vehicles, primarily from NASA, but also from ground-based sources and from sort of hybrid sources like GPS. I mentioned disruptions of GPS. We can use GPS measurements, now known as GNSS measurements, to infer ionospheric properties, and both space-based and ground-based aspects of that type of measurement, and using those measurements to try to tell us if our models are doing the right thing, if they're any good, or try to figure out what areas they need improvement. So model data comparison is a large part of it, and then communicating the results of that research, both in a specialized and general audience, preparation of talks for meetings, and writing results for publications. And then, of course, particularly as years go by, one becomes trained more in management processes, and in trying to organize teams of scientists. These giant models, I haven't said too much about our new approaches to this high resolution ionospheric thermosphere modeling, but a lot of it is built upon numerical processes that are used in the big NCAR climate and weather models. We can use a lot of those mechanisms at much higher altitude, basically moving out of the regime for which they were intended. And so consequently, you're participating in an enormous model development process, which takes very big teams of scientists, each working on different aspects of the process. And that takes a lot of organization, a lot of meetings, a lot of management. And so the reality is that, especially at a national center like NCAR, the reality is far from the canonical idea of the scientist working alone in his office, poring over equations, trying to make a contribution in a isolated fashion. It's a much more collaborative process.
That's awesome. And I know that you mentioned the Center for Geospace Storms with a lot more work that's going to be coming out in the next couple of years. So we definitely look forward to being able to follow your path and all of your collaborators, the work that comes out from that.
Many universities and other organizations are involved in that, and which is its own challenge for long distance work.
So I would like to just say thank you so much, Dr. Stan Solomon, for sharing an inside view of what are these space storms and some awesome photos of the field photos that you've taken yourself.
Thank you for the opportunity.
Great.
This lady here visited the Briars back in 2016. That's a picture down in the observatory with the 14-inch, and she'll talk about why the Apollo missions flew in a figure 8. So.
It's a question you guys have had and one I've had as well, so I'm finally going to answer it. Why does the Apollo trajectory look like a figure 8? So this is probably the diagram we're used to seeing. It looks like the Apollo spacecraft is tracing a figure 8 from the launch point on Earth around the moon back to a splashdown on Earth. Of course, what we're looking at here is the free return trajectory, not the actual flight profile, because that flight profile, of course, would include orbiting the moon and, in many cases, landing on the moon. Nevertheless, all the Apollo flights followed this profile. The question is why? Because some people often think that this is the opposite way you would want to go to the moon. So let's start with the Earth and let's pretend that we're hovering somewhere above the North Pole, such that we see the Earth's west to east rotation as a counterclockwise spin. Now the moon does the exact same thing, but as we know, one day on the moon lasts the equivalent of a month on Earth. Nevertheless, it is also making a counterclockwise spin from our weird hovering above the North Pole location. And a quick terminology lesson before we keep going, because this will become very important. The east end of the Earth from this orientation, so the direction towards which the Earth is spinning, is called the leading hemisphere. The opposite end, away from where the Earth is spinning, is called the trailing hemisphere. Keep that in mind. Because Apollo crews launched towards the east to take advantage of the Earth's spin to use a little bit less fuel to get into orbit, they all ended up orbiting the Earth the same way it spins, from west to east. Now, recalling that the moon rotates the same way, it would stand to reason that we take advantage of the speed and actually go from the west to east rotation on Earth all the way up to a west to east rotation on the moon. Well, turns out that's not exactly the safest way. So here's where it gets a little bit more complicated. Bear with me, I promise it's not actually that bad. When a spacecraft passes a body in space, and by body I mean a planet or a moon, not some poor unfortunate soul who's floating alone in space, let's hope that never happens, it gets what's called a gravity assist. This is basically a very small transfer of momentum from the planet to the spacecraft. That's because any planet has a much bigger gravitational pull than the spacecraft. We've all seen this happen with the Voyagers. Both Voyager spacecraft did gravity assists among the giants to get onto their next destination. Now, where the spacecraft passes the body is what's really important here, and this is why those terms of leading and trailing hemispheres become very important. If a spacecraft passes by the trailing hemisphere, it gets a bigger kick of energy. That's because it's gaining a little bit more momentum as it travels with the direction of the planet or moon's rotation. If a spacecraft passes by the leading edge, on the other hand, it's going against the direction of the planet's rotation. So while it still gets a kick of energy from that close pass by that moon or planet, it's a little bit less energy than had it gone by the other hemisphere. So let's go back to Apollo. Assuming a crew did absolutely nothing to adjust their trajectory, that means no burns with any of the engines and just left it all up to Sir Isaac Newton in the driver's seat. Let's say they then passed the moon's trailing edge. Well, they would get a much bigger kick into their momentum that would send them on a much larger orbit around the Earth that would take them either a lot longer to get back to our home planet or require a lot more fuel to adjust the trajectory to get back home. Now, as we know, fuel is one of the most expensive commodities on a space mission because it's so hard to get off the ground in the first place. So the simpler way to fly is always the one that uses less fuel. So this is where passing by the moon's leading edge comes in very handy. On Apollo missions, the crew passed by the moon's leading edge to take advantage of the smaller increase in momentum. This ensured that without doing anything at all, the crew would be able to whip around the moon's far side, and it would send them back on a trajectory that would intersect the Earth. So this would be very important if, say, the one main engine, the SPS engine, failed. They would be able to do this free return trajectory and make very small tweaks to their eventual impact point on the Earth, or where they would begin re-entry and landing, using their RCS thrusters. It was simply the safest way to get people to the moon and ensure that, as per Kennedy's demand, they return safely to the Earth. So let's break down what actually happened on an Apollo mission. When the crew did their translunar injection burn, the TLI burn that would send them from the Earth to the moon, they were not aiming at the moon at all. Remember that the moon orbits the Earth, which means that they were aiming towards a point where the moon would get in 3 days. So basically, that burn put the crew on a very high elliptical orbit that had its apogee somewhere around the vicinity of where the moon would be in 3 days. The spacecraft flies towards that point in space as the moon comes nearer, and when the two eventually meet, the moon's gravitational field becomes the dominant force and causes the spacecraft to whip around the moon's far side. Now, because the spacecraft is traveling by the moon's leading edge, it actually takes less energy and less propellant to slow the spacecraft into a lunar orbit, which is another major win when you're dealing with spaceflight. So from there, it was a simple SPS burn, or Surface Propulsion System burn, for the crew to slow to get into lunar orbit. The trans-Earth injection burn after the landing mission would send them on the same path back towards Earth. This ultimately traced out a figure 8. I really hope this helped clear up some questions for you guys. And if you would like to learn a little bit more about not only trajectories, but how Apollo actually navigated this course, definitely check out my friend Dave Wood's book, How Apollo Flew to the Moon. It is absolutely everything you never thought you needed to know about Apollo.
And now we'll look at why is there life on Earth and some of the key moments that have enabled life to arise. And this goes for about 2 or 3 minutes and then we'll close. And of course the molten core is what gives rise to the magnetic field that gives us the aurora. And with that I'll close the May meeting and hopefully we will see you at the June meeting. Thank you.